Good morning, everyone. My name is Anton Burman, and I'm a PhD student at the Division of Fluid Mechanics in Luleå, at Luleå University of Technology. And I'm here to present my work in Ume River, and I've been working with my colleague Anna, who can also introduce herself.
Hello, everybody. Welcome to the webinar. My name is Anna Juarez. I work in NTNU in Trondheim, in Norway. And together with Anton, we will present today the hydraulic models in Nidelva and Ume rivers. I would also like to mention Knut Alfredsen, that has helped me from NTNU to develop the model in Nidelva River. This is the general overview that we will go through today in approximately 20 minutes, and you can ask questions that we will be happy to answer at the end of the presentation. So first, I want to give a general overview of the problem, why of the project itself. So according to the Paris Agreement of 2015, by 2050, the European Union should cut greenhouse gas emissions to 80% below 90 levels. And according to the European Environment Agency, this is currently happening. The problem is that we have to improve even faster to achieve these goals. But if we look at the share of EU greenhouse gas emission by source of 2018 from the same source, 20% is due to the energy industries and 25% is due to the fuel combustion of energy industry. So we can say that energy transition is a fundamental step towards sustainability. And how is actually EU trying to achieve this goal? By increasing the wind and solar energy. If we look at this graph of electricity generation from renewable by source, we can see that hydro is one of the big sources, of course, but solar and wind energy are increasing even faster and faster. And not only this, the EU installed more wind energy capacity than any other form of electricity generation in 2018. The problem with wind and solar energy is that we cannot control when the energy is produced, and energy cannot be stored in practice. So production has to be equal to demand at all times. Therefore, this wind and solar introduce instability in the system that only hydropower can balance. Why? Because we can decide when to release the water storage in the reservoirs to produce energy. This is the context of our project, Hydroflex, that aims to develop a new technology permitting the highly flexible operation of hydropower stations. All this within excellent environmental and social conditions while being economically competitive compared to alternative solutions. And this is an overview of the work package that form this project and all the partners involved, quite a lot. I will not go into detail into this, but you can see that in work package 3, they will take care of the turbine study, and work package 4, generator and converter, and we are in work package 5, taking care of the social acceptance and mitigation and environmental impact. To study the impact, we should also mention one of the biggest impacts of the hydropower operation. One of these consequences of this flexibility is hydropeaking. But what is hydropeaking? Hydropeaking refers to release of water retained in storage reservoirs to generate electricity in response to variations in market demand. For instance, as we said before, because of intermittent electricity generation from solar and wind energy. And in practice, this is an example of a discharge variation in the outlet of a hydropeaked power station that has a high fluctuation on discharge in a very short period of time. And of course, they will have an impact for the ecosystem in the river. These are the sites that we have selected in Hydroflex to study this problem. I working from Trondheim, and Anton working from Luleå University. And now we will continue talking about the study sites.
So the chosen study site for me is the reach downstream of the Stornorrfors hydropower plant. Stornorrfors is, when you count in terms of electricity produced, the most productive power plant in Sweden. So And it's also pretty interesting reach in general, because a little bit upstream of Stornorfors is confluence between the Ume River and the Vindel River, which are two huge rivers in their own rights. So the area around Stornorfors has a lot of high flows compared to other rivers. So I have chosen the reach downstream of Stornorfors, and you can see on the figure here that there are two squares, one called the bypass river and one called downstream of the power plant. You can see the black dot that says outlet. That is the outlet of the power plant. So initially, the idea was to study the hydro-peaking effects downstream of the power plant, but at the start of this project, there was no geometry available in this point. So I have had to focus on the dynamics of the reach in the bypass river instead. So in this presentation, there will only be results from this reach, but a couple of weeks ago, Vattenfall did geometry measurements of the reach downstream. So after New Year's, I will have time to start working on that reach also. You can change, Anna. And since Anna has worked more with this site, she knows better, but the reach for Nidelva is the lower reach between, if you pardon my Norwegian pronunciation, Nedre Leirfoss and the Trondheim city center, or I guess even the outlet into the sea. And for the dry reach, the geometry has been measured in the winter time, because in the winter time, this reach is entirely dry. There is no water coming here, ideally. So that is a good opportunity to do drone measurements, which have been done. And I think Nidelva has been measured with ADCP, acoustic Doppler measurements. So they have been measured with a little bit different techniques, but I think they are both reasonably good. You can change, yes. The tools we have been using are two different simulation softwares. Anna has been using a software called Hekras, and I have been using a software called Delft 3D. Hekras is a free tool, but not open source, and Delft 3D is a free tool that's open source. On the left figure, you can see how a computational grid looks like in Hekras, and on the right side, you can see how it looks like in Delft 3D. There is a little bit of difference in implementation. Technically, in Delft, you will have something they call curvilinear mesh, where the computational grid follows the streamlines and the river, and in Hekras, I guess you have a traditional square elements. So they are a little bit different in implementation. We can change.
Yeah, and now we'll talk a bit about calibration of the models. How do we calibrate these models is through the Manning number. The Manning number describes the roughness coefficient. The symbol normally uses the letter N. And the roughness coefficient defines how smooth is the surface. So to put an example, it varies normally between 0.02 and 0.10, being the smaller numbers, a smoother surface. So for example, in this picture, we can see that the snow surface will have a very slow Manning number, going the decade faster as the water will go faster in the river. This table from 1959, you can see some of the values normally used, depending on the area, which we have a channel, a normal river, and so on. And how do we check the model with validation points? Validation data is used to check the reliability of our model. And here you can see the points that we have used in Ume and Nidelva. How do we actually calibrate is by running different simulations. With this information from the points, we run a simulation at different Manning numbers, and each Manning number will have a different water surface elevation, and we choose the Manning that better adapts to our model. And now Anton will continue talking about his results in Ume.
Yes, so on the left side here, the left figure, you can see how the water level looks like in the 8 validation points that you could see in the slides before. The points the more on the left, the more upstream they are in the reach. And it's worth to stop here and take a little discussion about some of the problems that are obvious with the, with the results here. If you look at the point most on the right and most on the left, they differ quite a lot. If you consider the straight blue line, this is the validation data. So this is the measured actual water level. And you can see that for 5 out of 8 points, it's possible to calibrate it in such a way that the water level matches pretty exactly. But for 3 points, this is not possible. And this is mainly due to uncertainty in measurements during the winter time, because in the winter, there will be significant ice buildup in this reach of Ume River, because there is no flow. There will be puddles of water that freeze entirely, actually. So there is a problem, and you will see it later more obviously in the contours I will show you. And on the right side here, in the right figure, you can see how the water surface looks like when it has been calibrated. So this is a calibrated model, and you can see for 6 out of 8 points, it's pretty accurate. Maybe less than a decimeter difference from the measurements, which I think is reasonably well based on how uncertain some of the geometries are in this reach. And the most upstream and the most downstream points are not looking very good, but that's mainly due to the ice buildup. In the next slide, you can change, Anna. You can see how the roughness distribution looks like in the reach. So you can see that there are points where the flow is very rough, and there are points where it's not so rough. And if you go back to the table Anna showed before, you would notice that in a traditional open channel flow, around 0.05 is considered like rough flow, and 0.1 is considered very, very rough. So I think it's pretty reasonable distribution overall. You can change on. Like I mentioned before, here I have plotted some contours. Basically, in the Ume River in the summer, you will, except when there is spilling from the dams, there will only be 2 different flow conditions. You will either have 50 cubic meter per second or 21 cubic meter per second. 21 is the minimum flow because that is what is passing through the fish ladder. And in the weekends, they increase the flow to 50 cubic meter per second so that the river will have more rapids and look more beautiful. So on the contours here, you can see how the water depth is and how the velocity is at 50 cubic meter per second. And on the left side, you can see the depth, and there are quite a lot of red holes where there is more than 5 meter depth, and this is due to the ice buildup that I mentioned before. In reality, this depth is maybe around 1 meter, but it's actually in the simulations like 20 meters, so it's not good. And it also shows in the velocity plots where you will have zones that there is almost 0 velocity, which is obviously unreasonable in a river like this. You can change on that. And here in the validation points in the summer, they have done some measurements of the water level. So what I have plotted here is basically how long it takes in each point before how long it takes before the water level changes to the next water level when you change from 50 to 21 cubic meter per second. So on the left side, you have the simulated response, and on the right side you have the measured response. You can change now. And here I have plotted the response in each of the points, and I have the overlap so you can more easily see how the model works against the validation. And in most of the points, they are very accurate, actually. So in general, the more upstream you are in the reach, the quicker it is until the water level settles at a new steady state water elevation. And the more downstream you are, the more diffused this wave becomes. And we also noticed that the more downstream we come, it sort of underpredicts how diffusive the wave is. So there is more improvements to be done in this model for sure. And in my future work, I will investigate more the properties that affect this damping wave and the behavior of it. You can change that.
Well, now I will continue talking about the results we have obtained in Nidelva. This is a table showing the results by comparing the water surface elevation with different Manning numbers with the validation data that I mentioned before. You can see it varies quite a lot depending on the Manning number. And finally, we combine the areas in which that have a better Manning number. You can see here 3 different comparisons that we did, and we cannot see it, but the final error is behind Anton, and it's 6 centimeters. So with those results, we could conclude that the model was well enough calibrated, and then we also did some other comparisons. He also compared the results with pictures taken in Norgay Bilde at 97 cubic meters per second, and we could observe similar flow patterns. From the results, we can also see that the lower most part of the river is mainly controlled by the tides, which varies between plus minus 2 meters over sea level. The average and high tide arrive up to Tempe, so you can see it in orange in the map, while the lower tide goes like in blue. So maybe there's around 2 kilometers difference, so it's quite a lot the effect of the tide in Nidelva. We can also see from the simulations that the lower tide areas, that the lower tide will create the biggest dry areas in the lowermost part of the river, as you can see here in this picture from last year. And we also, some other results we could compute is the dry areas depending on the charts. So in this table, we show the dry area depending on the discharge, and we take as a reference point 135 cubic meters per second. And as the discharge starts decreasing, the dry areas start appearing. 30 cubic meters per second is currently the minimum flow written on the license in Nidelva, but the discharge rarely goes below 35 cubic meters per second. And that is good because below 35 cubic meters per second, the dry area that appeared for every cubic meter per second reduced increases. So therefore, it's good not to go below these numbers. And you can see those dry areas shown red in the map. But we can take this data and go more into detail. And this model can help us to identify particular areas like this one. And we focus in one of the most interesting areas where previous studies show that fish stranding occurs because of hydropower. As maybe some of you know, fish stranding can lead to fish mortality. And this effect was studied here some years ago. This picture was taken last spring in May at 35 cubic meters per second, and you can see it's quite dry at low flow. And not only this, we could also see, I was there, and we could also see stranded fish in one of these pools. Also from this area, we will look into this side channel where I was there, also taking some pictures. And this is the discharge at 35 cubic meters per second. And less than an hour later, we could see the river almost full with the discharge of 130 cubic meters per second. So it's quite big visually to see it in the side when you are there, more than in a map, in a little red points. And yes, as I, coming back to the beginning, when I say I will show a video showing the effect of hydro peaking, you can see it here. That's several pictures that I took. They are taken in 45 minutes, less than an hour, in this side channel. And you can see how fast it increased and covering so big areas. And of course, the same effect happened the other way around when going from 135 to 35 cubic meters per second. So we are done with the results now. We can maybe talk about some of the future work that will be done from Hydroflex with this model. We want to test different operational scenarios that will be done by the Hydroflex group led in TU Aachen, the work package 2. This is an example that we did of an scenario of 30 start and stop. So you can see how it's like a heart pumping sort of, and it can happen really, really fast. We will also test the Accor air cushion underground reservoir designed by NTNU. Just a general idea is like a camera behind of us in this video, but like a camera that contains the water from the hydropower plant. And instead of releasing it like a wave very fast, like a flash, it will release the water in a smoother way. And then the fluctuation will not be as steep. And also the results from the models will be implemented in a fish population model, EBM salmon, that will be done by Nina. This is more or less the work that is going to be done with both of the models, but maybe now Anton wants to see something more since you are more focused now in your model.
Yeah, I think since there are now measurements done downstream of Ume River, and there have also been divers, so there should be pretty good validation data for the water surface at 4 points, I think, in the downstream reach. I'm going to investigate the hydropeaking like you have done here with the different operational scenarios. The people in Aachen have given us 3 or 4 scenarios, I think, based on different EU scenarios that they think are reasonable. So it will be interesting to investigate how that will look like downstream of Stonarfors. I'm also going to collaborate a little bit. There have been discussions, at least with an ornithologist in SLU about seeing how the hydropeaking could potentially affect like the bird life in the reach downstream. There are reaches that they have pretty significant population of, I guess you call it wading birds also, and they have ducks and geese and so on. And of course also focus on how it could affect the fish population, and vegetation maybe is out of scope, but it can be of interest also. We will see how well it goes. So it's basically the plans for how it will be in the future.
So with that, we can say thanks to the people seeing, and thank you for your attention, and see you in our webinar. Tusen tack.
Can you describe the money number in detail? Basically, it is like a friction factor for the flow. It comes from, there is an equation called the Manning equation, where you have a coupling between the flow and the water level, I think, and this Manning number. So it's basically the parameter describing how the friction is in a river. But there are also other alternative formulations of the Manning equation that has like a coefficient called the Chassis coefficient, and there is like other friction coefficients also that are not so established maybe in river modeling, but maybe on more fundamental fluid mechanical level, like equivalent sand grain roughness and stuff like this. But basically the Manning number comes from the Manning equation. Maybe you have something to add, Anna?
It was a pretty good answer. Yeah, it's basically what Anton said. I think I agree. Yeah. I don't think there is a way to actually measure the Manning number physically, but I think it's more than an invention to make the equation work in a way.
Yeah, it's dependent on the flow rate. Or in the Manning equation you have on the left-hand side, you have the flow rate, and on the right-hand side you have like the Manning number and like the gradient of the slope, and you have the hydraulic rate. I don't remember exactly, but you have a couple of different variables on the right-hand side. So if you want to measure the Manning number in a reach, you would have to measure all the other variables on the right-hand side.
Yes.
Okay, good.
And I guess I could also say that the Manning number is, the Manning equation is only defined for open channel flow. So it's a special case for open channel flow.
Hola, Rodrigo. Hello, there is Rodrigo asking for me if the solution of the cavern in Nidelva River to release water is a really interesting one. Has this solution been implemented on other rivers for this purpose? If so, has been cost effective? The design of the Accor air cushion under
reservoir
cavern and it's being done by another of the work packets here in NTNU. So it's just so you know, I'm talking for someone else in this case. I think it has not been implemented and is currently not cost effective because, of course, it has to be a huge cavern and that will take a lot of resources. And this is actually one of the main points that they are studying right now in NTNU, how to make such a cavern and such a innovative solution cost effective. So it's something that I encourage you to follow up, and thanks for your question.
Okay. Thank you again. If I don't see another questions, but I'm sure you could contact Anna or Anton if you have questions.
Yes.
I'm sure they will be open for that. So, here's another one from Chirag at the end. Do you follow any specific strategy for mesh size?
Well, I think that's different for both of us. In my case, it's a trade-off. I want to find the smallest cell size that I can, but I still do the computation time worth it. I mean, if the computational, Of course, it also depends on my geometry. Let's say that my geometry is defined for in a raster of 0.35 meter squared. Then my cell size will not go smaller than this because it doesn't make a lot of sense go smoother in the computation than the data that I have. But if we go over the resolution of my raster, it is a trade-off between how much time do I have to compute and how much accuracy do I want. And in Nidelva, we have gone for accuracy, of course, because we really want to look into these weighted areas as much in detail as we can and spending some more time. HECRAS has also the limitation that it's a maximum of 2 million cells, but in this case, that wasn't a limitation factor.
For me, I can't really say that I have had a strategy. One of the advantages I think that we have discussed with Delft over HECRAS is that you can run Delft on parallel CPUs. So, and I don't think there is an upper limitation of the mesh size. So there is no valid excuse maybe for not doing a proper mesh study. But I think for myself in my future work, when I'm working on the ridge downstream, I will definitely try to do some sort of Richardson extrapolation to find the most reasonable mesh size. But this hasn't been done yet, but I think it will be done.
Okay, thank you very much, Anna and Anton again, and I think we'll close the webinar here. So again, thanks everyone
Thank you for the questions.
for watching.
Thank you for the questions.